Welcome to Renaissance Charge Videos. I'm Rick Friedrich, and today we're going to be looking at the new mini window motor. So in the past we had another window motor, which is represented here, one of the models that we made with 18 gauge wire, and this was a watercraft remote control that I made. Whoa! Anyway, I dropped it the other day. Anyway, this is six magnets on this rotor, which wasn't enclosed, so we had to put the string tape on it. Now we're making it improved, where the rotor encases not just 6 magnets, but 8 magnets. So it's 8 poles, and it pulses 4 times per revolution. So again, what these motors do is they charge another battery while they're running off of one input battery. Now I could charge up higher voltage batteries than the input. Say this is 12 volts, I'm charging 12 volts right now, well, I will be when I turn it on, and then I could actually charge 24, 36 volts. Now I do have circuit protection on here that activates at about 46 volts. It flashes over just in case I disconnect my charging battery. Those are gas discharge tubes in there. So the idea of this motor is that we can have free energy and a charging battery while we're running the motor. Now in this case we're going to do a little bit more than that, but first of all let's describe it a little bit more. So what we have here is the ability to put 8 coils on here. Now this is going to come for $120, $115 with the single circuit unassembled, $120 for that circuit assembled. Now the rotor will always come assembled. It's kind of dangerous. We have to press the shaft in. And then for $140, you have an unassembled board for 4 circuits and 4 coils, so adding 3 more coils and 3 more circuits, like you see here. Or assembled board for $10 more, $150. So we are 3D printing these different colors. We've got red, really nice red, kind of glitter red and a glitter blue. If you want some specific color, let me know in the ordering. You can make a little note there. This was a previous test model with a different material in gray. It's not really usually going to do. We're going to probably make this in white and different colors. Whatever material we have, we print this ourselves. So what happened was we ran out of the inventory on this first model, and I just kind of let it go for a while. But then I decided I wanted to show people, give people the opportunity to experiment with the output. Now this is negative energy engineering. Negative energy is the opposite in so many ways of what people are normally used to in positive energy. So that is positive energy charging has dissipative energy, it's current, and it's wasted energy. You can measure that with an ammeter. With negative charging, This is normally disregarded, except for my motor systems. There's a few other people that might utilize this energy in different forms, but we've done this for years in various motors. This being one of the ones that we've done for many years, although this is a newer model of it. So now, what we can do along that charging negative path, the negative energy, you should say, converges in to the resistances or the wires and the battery plates and so forth. So it's not positive resistance, it's negative. So it's opposite in every way. Now along that path to the charging battery, what I have here is just a basic version of what I call the third stage process. This is one of the reasons why I'm bringing this motor back into focus, is because it's the most affordable motor that we have that you can test. And if you do experiments, you could easily replace those transistors, especially if you just have the one single coil, single circuit. And that way, with the bigger motors that we have, you're not experimenting first on those with this process. So this is what I call the third stage process. The first stage was just to charge another battery in the most basic sense. The second stage was to actually run more batteries in a different configuration. The third stage, what I called, it wasn't really any particular order to the numbers. It just so happened to be the next thing that I was focusing on with this loving path, selfish circuits loving path teaching. So the third stage was running series impedances, ideally the Tesla one wire circuit, which is a resonant circuit in series, well, not even in series, really in parallel with the wire going to the charging battery. In Tesla's case, it was a ground or a copper bar representing the ground. And the Tesla impedance circuit, which my friend called the hairpin circuit, that kind of concept can be done with what I'm doing here with these bulbs. So in this case, I'm going to be running, instead of parallel to the one wire, so we'll say this positive connection to the charging battery here. Oops, on this side, this is the charging battery. We're going to run in series with that terminal just along the one wire. We're not using the other negative terminal of the battery. We're going to run a bunch of inductors, as you can see in this one box. The inductor. And then we're going to put the bulbs, which have bridge rectifiers and capacitors in them. They're going to be in parallel with the bulb. So this is not the ideal setup, but you'll see, I wanted to show on the scope, as we turn each one on, the voltage across the transistor is going to rise up. So let's look at all that. Let's turn on the batteries. And we'll just start everything up. It's not self-starting. You can turn it in either direction. So we'll let the voltages stabilize a little bit. And then we'll begin turning on in a specific order. So you can see the bulbs are really bright. You can watch as the oscilloscope voltage rises. And then we're going to get actually too high to actually see the top eventually. We'll have to change the settings. So we're at 200 volts, well 150 volt divisions. So the charging rate in this less than ideal situation does go down as we add more of these loads. So it's like adding more batteries in series. So this is not in resonance here. So ideally, we would be running this in series, well, actually in parallel with the wire in the various circuits, as I talked about in the True Wireless 1919 article that Tesla wrote, which was very important. Let's turn this off. So in that article, I just want to be heard. I don't want to be making it hard to hear. So in that article, Tesla wrote that we could run a one-wire circuit and actually power loads, resonant circuits in parallel, various kind of parallel or perpendicular to the wire in figure 5. You have to combine figure 5 with figure 10 to understand the full circuit. So I showed that, kind of clarified it a little bit more than the article shows in a separate paper, which I've handed out. So anyway, what can be done there, this is where I'm recommending with this motor to test these things out, that you find the resonant frequency, so the operating frequency of this motor, which is set by the 330 ohm resistors, which could be changed. You could put in series with all those resistors another variable resistor, potentiometer, and adjust the frequency, or that would lower the frequency further. You could change those to maybe 220 ohms, push it a little bit harder. But that's what we provide right now with the circuit, because it was more of a sweet spot arrangement there. So you can find the RPM, and with that you can develop, with the right inductance and capacitance, you can find the resonant frequency, or combined with the frequency that this puts out, you can then create a resonant circuit. And if you do that in series with the charging battery, what can happen is you can create a setup where you can add as many of those circuits with corresponding loads as you want, as we've shown in previous videos with the black box. So that's what's in the black box, but there are different variations of those circuits. So here we're showing just throwing together some inductors. There are no particular special inductors or anything. They're not matched to anything here. They're not in resonance. So they have limited benefits. Now what happens is, you can see more about this in my previous videos on selfish circuits and loving paths where I get into it in more detail. But here I'm just talking about the basics. So in this case, we do have some added benefits. It is true that as we turn on more switches, the charging rate of that battery gets less, and altogether the bulbs dim a little bit more because we're not doing a resonant circuit. However, you can see the voltage across transistor increasing as we turn on each additional one. So there is energy going back to the input in that case. Now it can get to the point where it's too much and it will damage the transistors. That's why I have the protection circuit on there. But there is a limit to that too. Anyway, what can happen is we have the input battery not discharging as we showed, but we want to have the true resonant circuit there, and we want to load down that circuit as well. So when you do it in parallel rather than in series like we're doing here, then you can have a lot, more isolation there and less kind of destructive forces coming back to the input side of the circuit. So we can have the input battery charging. We can ideally have the batteries just sit where they were at. Now this is what we showed in Chicago in that black box, and in Hamburg many times 5-6 years ago. So again, I just showed this years ago on the basic level so people could play around with it. Now with the other 4-pole, I've run many inductors like this and powered numerous loads and bulbs, and these kinds of systems have powered whole shops. So they really are, they make this whole thing a prime mover in which you can add as many resonant circuits as desired because of the negative energy. So while high frequency circuits allow for really no losses because of the skin effect and so forth, this is different because this is the negative output. It's the impulse technology plus it's the negative energy, which is different in characteristic than the positive, as I mentioned. Because the energy is converging in, there are obviously no losses in that. So the whole path, if you will, the energy converges in. Instead of pushing current down that path and having your losses, therefore, you have the opposite experience. So it's kind of hard to even come to grips with until you experience it. So this is why I've provided this bigger kit at this time to be an affordable way to play around with this, and we can easily replace these $2 MOSFETs, or these are transistors. You can get higher quality ones if you want to get a little bit better gains and higher voltages, but this is what we're providing because I want to make it affordable. Now we do include some lube. This allows the bearings to never wear out. This is Bishop's oil, and we sell that, but I include that on the bearings when we assemble it. Now we don't assemble the frame unless you pay for that. As I said, there's unassembled and assembled. And the other thing is, I think we're not going to put the motor wires into the board either. We'll let you do that. And then the assembly of this rotor, you have to, well, we'll show that in the instructions. So we could run this again. Let's see. See, it goes into oscillation. But what's really neat for some reason. What you can do, if I can get this position right. I don't have the spacers in this one, so anyway, you can run two rotors at the same time. I don't have it right set up here. That's kind of fun. It's not really the purpose. Now, one other thing I want to mention is that we will be doing versions of this a little bit down the road. We've got to catch up with a lot of orders right now. And once this video is posted, there's going to be a lot of orders for this. So I'm not going to do it just right now, but we'll do 18 gauge wire again, and we'll make the Hall circuit there. But we have to create more frame support. Now in the ends of these, you can see we have machined or designed nuts to be fitted in there. Now we're not providing that at this point, but they can come out these holes here. Well, the bolts can screw into the nuts, and then you could mount. What we were initially going to do is an opto sensor, but you can also mount Halls on there, is what we'll do. So that we're not trying to, the problem with using the Hall sensors to switch this on the main rotors themselves is that you have the interference of the coil magnetic field. It becomes very difficult. When I made this, it took me a while to position those Halls just in the exact spot so that it could always self-start. So we can make a self-starting motor, but it does not have the advantage of the trigger coil in that case. The trigger coil gives you some added output, as I mentioned in the last video, where there's three outputs in this kind of system. One is powering the motor in its own circuit loop. The other one is charging the charging battery in that kind of side loop. So this is part of the Tesla shuttle circuit, where you have an independent body that's out of phase with the motor circuit. And then you have another circuit, let's say on the other side, which would be the trigger coil. And that represents an equal amount of energy, which is dissipated in the resistors. Resistors then are utilizing that load, as well as the bases of the transistors. Now we can engineer that and get more energy out of that, but that wasn't the purpose of this particular video and demonstration, but we talked about that a little bit in the last video with the fan kit, where we were running a bulb in series with the resistors. So we will, like I said, make this available at some point in the next 6 months perhaps, where we can make this a torquey little motor with a bigger gauge wire, or you can run this at higher voltage. Now this previous model, we were running this up to 30,000 RPM, but there was no real protection on the magnets. We had to put nylon tape around there and crazy glue. So now they're fully encased, you can't even see them. You can run this a lot faster. Now the thing about these coils is you have to position them just right. So it is a kit, it's something that you play around with. And then you can fasten them to each other if you got the 4 of them, and you can fasten them to the support bolts all the way around. And then you can make your own frame, space support, however you want. Some people will glue them in when they've got them. So what you have to do is place, if you're looking at the rotor, if you can figure out where the magnets are, because you can't see them anymore, what you need to do is make the center of each of the windings here, each of the coil, if you were to look down to the shaft, you would want the center of the magnets and the center of the coils to be lined up with the shaft on either side. So the further you go out, the more you'd have to pull these apart in order to get that. Because what happens is the field is spinning this way, and it's kind of turning the rotor, and then so you have, say, a north pole being triggered, turning on the the trigger wire, turn on the transistors. So you have a north and a south at the same time, because the magnets alternate between north, south, all 8 of them, all the way around. So ideally you want the right spacing, the width of the magnet, the face of the magnet, and the amount of wire and all that. So it's about positioning it a little bit higher and lower just to get it right. So that's all I'll say for now. You can look at previous motors. Oh, the other thing was the reason why it was called window motor by Bedini, which actually this isn't anymore, and for lack of a better word, everybody's used to that, so I continue to call this that. The window would be wrapping the coil all the way around the rotor, which is terribly inconvenient and unnecessary. That does not provide any more gain, as Bedini and Newman, who Bedini got the idea from, and the Newman motor, both of those men insisted on wrapping it around, which you'd have to then wrap it around the shaft, and that is unnecessary. So that's why he called it a magnetic window motor, because it was a window around around the rotor. So for lack of a new name, I'm just going to leave it at that. So thanks for watching.